Okay, so we just have one topic left to cover from chapter 8. And then what I'm going to do, I think we'll have even a little bit of time today, is to start on chapter 9. Now, chapter 9 is that assignment or that objective, to use the Alex terminology, is extra credit. So it's not mandatory that you do it, but it is extra credit. So if you want to get a few extra points on your homework, you could use that to do so. And actually this morning I created another extra credit assignment, which is a couple of other topics from chapter 9. And so again, that one is also optional, but I'm hoping I'll have enough time to cover those topics. They're useful topics if you're going to go on to take organic chemistry. Okay, so let's finish up the last topic from chapter 8, which is what's called bond enthalpy. Okay. So let me bring this up here. Bond enthalpy. It's section 8.9. And it builds on all of the Lewis structures that we've done. So the nice thing about this topic is that although you're doing Lewis structures in it, they're the very simplest of the Lewis structures, you know. The Lewis structures are, some of them are really simple. Like if you do H2, that's really simple. O2 is very simple, N2. They're very easy to do, you know, octet rule for them. Don't really need to worry about formal charge calculations. You just got to do the octet rule. And even some of these like NH3 ammonia or H2O or CH4, these are really easy Lewis structures to do. You don't have to worry about expanded octet, that kind of stuff, okay? So bond enthalpy, we're really just going to be dealing with some of the simpler molecules, some of the simple organic molecules, and then water, hydrogen, nitrogen, ammonia, stuff like that, okay? And so let's take a look. So let's remind ourselves that when you have two atoms, so let's take the hydrogen atom just as an example. You know, we draw the Lewis symbol for the hydrogen atom to look something like this, right? But let's remind ourselves what that is, right? The symbol of H is there to remind us that we're talking about a specific element, right? A specific atom, which is hydrogen. But hydrogen is the simplest, it's certainly the most plentiful element in the universe, but it's also the simplest element in the universe. All it is a proton, right? A little proton, I'll draw it like that. There's your proton. And then a little electron that's somewhere near the proton, right? And whether you want to use the nuclear model of the electron orbiting, or more accurately, the quantum mechanical model, right? So the quantum mechanical model is not that this electron is like some particle that's going around in circles. It's that it's a wave that occupies some volume around the proton, right? So I'll draw it as little dashes here, right? So here's your, for example, your 1s orbital, right? Right, there's some probability distribution that the electron occupies, but it's some sort of vibration, right? Some sort of vibration that, you know, is difficult for us to conceive of, but it's a type of vibration that the electron is undergoing or exists as around that nucleus. So there's your atom, right? So essentially what we're claiming is that what happens when you build a hydrogen molecule, so here's one hydrogen, here's another one right there, that those two electrons are going to pair up. And so what will happen is the two electrons will now occupy the same space. And this is now our H2 molecule, right? So you have two hydrogen atoms that are separate, each with one electron. Now you have two hydrogen atoms that are somehow associated with each other. They're connected to each other in some way. They stick to each other. And the way they stick to each other is through these electrons. And that's not necessarily intuitive, because if you think about it, electrons are supposed to be repulsive with each other, right? They're supposed to repel each other, right? But somehow, let's use line notation, somehow those two electrons quantum mechanically are associated with each other according to the Paw Exclusion Principle. They occupy the same space, but they have opposite spins, and that allows them to interact with each other. So here's what essentially happens. So this is just one hydrogen atom. What happens when you take the two of them and you put them together? Okay, well, here's your nucleus for the first one. Okay, there's the electron, right? Where's the electron? It's somewhere around there, right? It's occupying that space. Now let's take the second hydrogen atom. It's the same thing, right? It's just a proton with its electron. So I'm going to draw its, I didn't draw that very well, did I? Let me do that one over again. I'll draw a little closer. There we go. So here's its atomic orbital, the 1s orbital, right? But remember, it's just a probability distribution. Okay, I'm trying to make these orbitals be the same. Right? Actually, they're 1s1, right? If you do the configuration, it's just one electron in a hydrogen atom, so it's 1s1. Look over here, you've got this region which these two orbitals are overlapping with each other. Right? So I'm gonna shade that in darkly here. This is called an overlap region. Those two orbitals are occupying simultaneously the same space. The Paw Exclusion Principle says essentially that cannot happen unless there's some difference in their quantum numbers. And so the difference in those quantum numbers is one of them is spin up, ms equals plus a half. The other one is spin down, the other one's minus a half, right? That's the difference. But we now have these two electrons occupying those two orbitals, occupying that space simultaneously. And here's what we can claim. We'll claim that since these electrons are negatively charged, they are going to be attracted to both of these nuclei, right? The nuclei are positively charged, the proton. So what essentially those electrons are doing is they are now holding those two protons some distance apart, right? Because they're both negative, both electrons are negative, so they're attracted to both nuclei. They don't have a preference for this one on the left. They don't have a preference for this one on the right. They have a preference for both, so they're holding them together. So even though the protons want to fly apart, the electrons in that region in between them are holding them together. Now, they can't hold them together rigidly because the protons kind of want to get away and the electrons kind of want to get away from each other as well. So it ends up vibrating. It ends up doing something like this. They're sort of, they're trying to get away, but they can't. So it keeps kind of going back and forth. And actually, these molecules, we can measure them. They vibrate like so, like a spring, right? If you had two masses on a spring, you could vibrate it back and forth. And that's essentially what happens with this molecule, okay? That's something that can be measured. Now, the question is, how strong is that attraction? How strong are these bond, or is this bond, we'll call it a bond, a chemical bond, between the electrons and the protons, right? So, it's not a simple issue, right? Because if you think about it, the protons are trying to get away from each other, the electrons are trying to get away from each other, but because the electrons are stuck in this orbital, the next highest orbital is pretty far up away from it. Overall, it's attractive. And so what we do is we measure how strongly attracted they are, and we use the term bond energy or bond enthalpy to describe how strong the attraction is between these two atoms. And so experimentally, what you would do is you would say, how much energy does it take if I have to put in some energy to actually rip that bond apart, to actually make the two atoms fly apart from each other, right? Now, remember, when we talked about this back in chapter 6, you have all these orbitals, right? And they get closer and closer and closer. Eventually, you get to a point where the electrons are no longer attracted to the nucleus, right? That's way up here. We call that ionization. So if you can get the electron up to here, it's just no longer associated. Well, you can do something similar here. You can put in energy to the point where those two atoms fly apart, and we would describe that as H plus H, right? So now each atom has its own electron and they're separated. The amount of energy required to do that is called the bond energy or the bond enthalpy. Since it takes energy to do that, it requires energy to do that, that's an endothermic process, right? It's endothermic, meaning you got to put the energy in to break that bond. And you can think about, like, just take a piece of chalk, right? You have to put energy in to break the chalk, right? It doesn't just break, and you have to put the energy in. So when you put that energy in, you're essentially breaking chemical bonds, and the calcium and phosphorus and oxygen bonds are breaking, and so it snaps, right? So you've broken chemical bonds. That's an endothermic process. Okay, so let me make a couple of points about this. One is the energy of a chemical bond is typically called bond enthalpy. Okay. 2, breaking a bond, a chemical bond, is endothermic. Right? Takes energy to do that. Likewise, forming a bond, this one's not as intuitive, is exothermic, right? That means it releases energy. Okay, so to put this in perspective, what that means is if you have a piece of chalk and you break it, right? You put in energy, you now break it into 2 pieces. You had to put the energy in, so that's endothermic. On the other hand, the reverse of that would be that if you took 2 pieces of chalk and you formed 1 piece of chalk from it, that would be exothermic. So it would release heat. Heat would come out of that process. Now, it's not easy to do that because what happens is the nature of chalk is that it's an ionic compound. And so in order to get the pieces of chalk to go back together, you would have to fit them so to the atomic level, you'd have to sort of align them perfectly. Furthermore, when you break it, oxygen and water in the air will immediately react with the surfaces and make those surfaces unavailable for reaction with the other piece of chalk. So in practice, you can't really do that. But we have many examples of chemical reactions where the opposite is exothermic. So here's an example. There's 2 processes in nature. One is called photosynthesis. And photosynthesis is where you take carbon dioxide and water and energy, right, in the form of light. Now, the symbol for light energy is H nu, okay, or HF if you want. Let's use HF. H times frequency, right? Because the energy of a photon is H times frequency. And then you get what? You get this molecule called glucose, and you get oxygen. And that's photosynthesis. So that's an endothermic process. It takes energy. You need the light to do that. Energy has to go in. But the opposite is called combustion or metabolism or catabolism, I guess. So that's where you take the glucose with oxygen, right? You need oxygen to burn things, right? You get carbon dioxide back out and you get water and you get heat. It's an exothermic process. Okay, so the reason for that is that when we break bonds, breaking a bond requires energy, but forming bonds releases energy. It's an exothermic process, okay? So if you look at this as an exothermic process right here, essentially what happens is when this reaction occurs, you're breaking a bunch of bonds here. That's what's happening. You're breaking bonds here, and then you're forming bonds here. And if the bonds that you form overall, all the bonds that you form, so all the carbon-oxygen bonds and oxygen-hydrogen bonds, if they are stronger than the bonds that we broke, then that process will be exothermic. Likewise, if the bonds that you're breaking are stronger than the bonds that you're forming, then that process will be endothermic. So by looking at whether something's endothermic or exothermic, you can immediately tell whether the reactant bonds are stronger or the product bonds are stronger. So exothermic means that the products have stronger bonds. Endothermic means that the reactants have stronger bonds. It takes more energy to break those bonds than you're going to get out, and so that's endothermic. All right, so let's take a look at how we go about this. A lot of data has been tabulated, and so here's an example. The energy required to break hydrogen into 2 hydrogen atoms, we're going to call that delta H. That delta H is approximately 436.4 kilojoules per mole. Those are the units we're going to use. Those are the energy units we used way back in chapter 5. We're going to use the same units here. In other words, in order to break 1 mole of the bonds between hydrogen atoms, a mole of hydrogen, H2, it takes 436.4 kilojoules, okay? So we're going to call that the bond enthalpy. And it's something that's measured, okay? So let me give you a few values, okay? Here's an example. To break an oxygen-oxygen double bond, right? I'm going to write it as 2O, right? You're breaking them up into 2 atoms, so 2O. The delta H for that one is 400. I'm going to put plus just so we know the sign. 495 kilojoules per mole. Now remember, it's going to be positive because breaking a bond is endothermic, right? So it's going to be positive. Let's try. So we got the H2, we got the O2. Let's do this one. The carbon-oxygen double bond. Breaking that bond into 2 separate atoms, carbon and oxygen, is plus 393.5. Again, kilojoules per mole. Okay. Here's another one, the OH bond. To break an OH bond into an oxygen and hydrogen atom, that delta H is equal to 463 kilojoules per mole. Depending on what table you look at, you might see 460, 462, 463, 464, but somewhere around there. Okay, so there's another one. CH, this one, to break this bond into C plus H. Delta H for that is 414 kilojoules per mole. Okay. Now, what about a carbon-carbon bond? What about breaking carbon into 2 carbon atoms? Well, that one is about 347. And now I want to show you something. What if it's a double bond? If it's a double bond, it's a stronger bond because there's more atoms, more electrons holding it together. So this is a double bond. It's actually what happens is it's more. It's like 621. Who's up? So a double bond is stronger than a single bond. Okay, it takes more energy to break it. And then what happens if you get up to a triple bond? Well, it gets even stronger. even stronger, right? So a triple bond in, between the same atoms, a triple bond is stronger than a double, and a double is stronger than a single. And that should make sense, right? Because if you have more bonds between the atoms, it's going to take more energy to break the relationship between those two atoms. Okay? So
I'm sorry, Professor. When it's 3 bonds, it's still gonna be 2C or it's gonna be 3C?
still 2C. There's only 2 atoms, right? So we're
Oh,
counting
okay.
that. Yeah, we're not counting the bonds, we're counting the atoms, right? It's a chemical reaction, right? So, in a sense, it would look like this. C2 goes to 2C. That would be the chemical equation, right? Okay. All right, so let's take a look at a problem. I'm going to see if I can pull one up here from Alex. And this is called calculating the heat of reaction from bond energies. Okay. So again, this is section 8.9. So here's what they do. They give you a balanced equation. By the way, these calculations are all done in the gas phase because the values of these bond energies or these bond enthalpies, they're all measured in the gas phase. They would be different if they were solid or liquid, and there aren't really tabulated values for solids or liquids. They're not easy ones to find. So they're all going to be gas phase. Okay. Now for this, you're going to use your data button from the Alex, toolbar. So, just look that up on your Alex, okay? So let's take a look. Here's how you do it. Essentially what you do, step 1, is you draw Lewis structures. Okay, so that's why this is in chapter 8, right? We couldn't do this without drawing Lewis structures. So that's your first step. So I'm going to do that first. Let's do our H2. So I'll put 2, and then I'll put a little parentheses there. The Lewis structure, I'm not going to spend much time on this because you'll be practicing Lewis structures. There's the Lewis structure for H2. It's pretty simple, right? And then I'll close the parentheses. So that 2, I'm going to put out here. We're going to need that in our calculation. But there's the Lewis structure. And then I'm going to add that. We got O2. There's only 1, so we just have to draw 1. So let me put that in parentheses just so that we can see it. Now, again, I'm not going to go through the details of drawing these Lewis structures because that's stuff we've covered, but you're going to practice these and you're going to get good at drawing Lewis structures by the end of this chapter. So there's your O2, right? So octet rule for oxygen, right? And then same thing, but now we have 2 waters. So let me draw the Lewis structure for water. The Lewis structure for water looks like this. Okay. Okay, so keep in mind, I'm putting parentheses around the Lewis structures just so that we know, really so that we know how many there are, because we want to indicate from the balanced equation how many bonds there are. Okay, so 2, I can put a 1 here if you want, 1 times that. Okay, now what you do is you look up the values. I'll just call them delta H values. You look these up. And be careful, these are not the delta H values that you did back in chapter 5. These are not the heat of formation values, right? These are what we would call bond enthalpies or bond energies. So let me write that down. I actually sometimes get the numbers confused myself. So, or bond energies. So let me be careful. I'm going to actually open up the Alex tab. Just make sure that we use the same values they're using, because I'm just looking back at that example I gave, and it's possible I even made a mistake with that one. So let's take a look. So I'm going to look them up. So what you do is you make a little table for yourself. So you put your bond and then put your value of delta H. Okay. So there's a hydrogen-hydrogen single bond right there, right? So you look that up, and it's the Alex actually just says 436. It doesn't actually give you the 0.4, which is perfectly fine. Just use the value they give you on Alex. Then come over here. The second one is a double bond between 2 oxygen atoms. So you look that one up, and that one is 495. Okay. Now you come over to this one, and you've got an OH bond. And that one, the OH is 463. Okay, so those are the three bond energies or bond enthalpies that you're going to look up from the table. Okay. And again, it looks like Alex doesn't go to point, which is perfectly fine. All right, there's our values right there. So now let's do this. Now what we're going to do, step 3, is we're going to calculate the sum of the delta H values for the reactants and products separately. You're going to do them separately. Okay, so you do them, reactants and products. So let's do reactants first. Now, this is where you got to be careful, okay? It's just arithmetic. It's basic arithmetic. Okay, so you have an HH bond. That's 436. But you have this 2 in front of it. That means that there's 2 of them, right? When I write 2HH, what I mean is HH and another HH, right? There's 2 of them. So that means that you're going to have to break, this bond here, but you're going to have to break that bond there. So it's really 2 times 436, okay, because of that 2. If that was a 3, then we would write 3 times 436, okay? Now, there's only a 1 here, so that's easy. O double bond O is 495, okay? So there's our reactants. So it looks like it's 2 times 436, which is 872, right? Plus 495. So it's 1367. I'm going to leave the units out just because I don't have enough room here. Now you do the products. Okay. Now on the products, there's just one product, it's water, but keep in mind, this is where it's tricky. You've got a bond there, that's the OH bond. To break that bond, or to form that bond actually, it's going to be 463, right? But there's another one over here, there's 2 of them. So that's 2 times 463. However, there's also 2 waters. There's 2 of these complete, compounds. So really you have 2 times 2 times 463, right? Keep in mind the 2 times the 2. Why? There's a 2 here, but there's actually, you have to break both of those. You have to form both of those bonds. So 2 bonds, but 2 waters, that would be 4. So 4 times 463. Okay. So 4 times 463 is 1852. Okay. Now that's step 3. So step 1, draw Lewis structures. Step 2, look up the values of the delta H's from your Alex data tab, or wherever you're going to look for it. And then step 3, you add up all the delta H's for the reactants, all the delta H for the products. There's one more step. Okay, so I'm going to write it over here. Sorry, I ran out of room. So step 4 is to find delta H, you do the delta H of the reactants minus delta H of the products. Now that might be confusing. Why reactants minus products? Didn't we learn back in chapter 5 that we do products minus reactants? And the answer is, what happens is we aren't breaking these bonds over here, we're forming them. So that changes the sign, right? So notice these are all positive values. They're positive when you break the bond, because that's how they were all measured. But in the products, they're actually getting formed, so the values are negative. So instead of doing products minus reactants, you do reactants minus products because the sign is the opposite of what it would have been, right? So here's what we would get then. Reactants minus products. So that's 1367 minus 1852. Okay. Remember what I said was that if the products have stronger bonds, it'll be exothermic. And if the reactants have stronger bonds, it'll be endothermic. In this case, the products have stronger bonds, 1852. Those are stronger. The reactants are 1367. That's weaker overall. So what happens then is you're going to get a negative value, which is exothermic. So 1367 minus 1852, and it's negative 485. Now that's actually pretty interesting. That's not too bad. Let me just check those numbers. The number doesn't seem right to me. So let me just check. 2 times 436 plus 495, 1367. So that's right. 4 times 463 is 1852. So that's right. 1367 minus 1852 minus 45. Okay, so that's good. So there's your value right there. Okay. Exothermic, right? If it's negative, it's exothermic. Which means that if you do this reaction, you get energy out, you get heat. So that means you could use this to form electricity. In fact, that's what some rockets do this. They use hydrogen as the fuel. They use oxygen as the oxidizer. And you get energy out. So that means you're going to get, energy that you can use to propel the rocket. Okay. And people have talked about actually making automobiles that are, instead of using gasoline, would use hydrogen and then use the oxygen from the air. And then the advantage of that is that your product is pretty clean, right? It's not carbon dioxide, it's water. And it's, water's a pretty safe product. So you get energy out of it. Okay. All right. So let's try another one. Okay, this one's interesting. So this one, again, everything's going to be gas phase, is CCl4. I'm just going to write, I'm not going to write that it's gas, but everything is a gas for these calculations. Okay, CHCl3 plus HCl. Okay, so here's one's a little different. We have, some chlorine in here, so it's going to be a little bit different. Again, the first step is to draw the Lewis structure. Okay, so let's go through it. CCl4, that's one we haven't done before. 1 carbon, 4 chlorines. So we're going to put the carbon in the center. We've got 4 chlorines, so those will be the surrounding atoms. Okay, got a hydrogen. Oh, I haven't finished the Lewis structure, sorry. So carbon is in group 4A, so it has 4. Chlorine is in group 7A, so it has 7. So 4 plus 4 times 7, right? There's 4 chlorines, so that's 32 electrons. We've already done 4 bonds, so we've already used 8, so that's 24. Distribute them as lone pairs on the surrounding atoms until you run out of electrons. If you have any extra, put them on the central atom. That's our technique. And then if the central atom doesn't have enough, then you form a second bond with one of the surrounding atoms, or 2 bonds if you need to. But it works out perfectly. That's 24 right there. So we're done. Octet rule for every element. Cool Lewis structure. Okay. So right there, that tells us we're going to have a carbon-chlorine bond. That's going to be important. Okay. H2, we just did that one, right? That one's easy. Now, what about this one, CHCl3? Well, take a look at what's happening. Essentially what's happening is one of the hydrogens is getting added to the carbon. So you're removing one of these chlorines. So you have CHCl3. So you're just replacing, the hydrogen is replacing one of the chlorines. So really you're going to get the same Lewis structure. It's just you're going to have a hydrogen and 3 chlorines instead of 4 chlorines. If you recall, when I talked about organic compounds, if you have CH or CH2 or CH3, the H that comes after the C is a surrounding atom on that carbon. Okay, so then we have HCl. So let's complete these Lewis structures. You got, again, carbon has 4 valence electrons. Hydrogen only has 1, it's in group 1A, and then you got 3 chlorines. Okay, so 21 plus 5 is 26. We've already used 8, so you got 18 left. Okay, so then you do the same thing. Pairs around the surrounding atoms till they get up to 8 electrons. And that works out perfectly. And then HCl is pretty easy because hydrogen's in group 1A, chlorine's in group 7A, so you got 8. We've already used 2, so you got 6. Put them on the chlorine, and now there's your Lewis structure for that. So those are our Lewis structures. So step 2 was you look the values up in the, you identify the bonds and look up the values in the table, right? So we have a carbon chlorine, we have a hydrogen hydrogen. We already know that one, 436, right? We have a carbon chlorine again, so that's the same bond right there, carbon chlorine. And now we have a carbon hydrogen. I think I said that was 414, but let's check. I'm going to use the value from Alex. And then you got a hydrogen chlorine. That's a different bond, ClH or HCl. So you got to look that up, right? So there's 2 of them that we did from, well, actually, we got to look up the CH as well. We'll look them all up. Okay. So let's see. It looks like the chlorine, I'm sorry, the carbon chlorine, looking that one up, is 328. The hydrogen hydrogen, of course, is 436. Okay. The carbon hydrogen, okay, so they use a slightly different value. They say it's 413. So let's make sure we use their value. And then the chlorine hydrogen is 431. Yeah, most of them are in like the 300 to 400s, right? It's when you get up to the double bonds, you get up to like 500, 600. Triple bonds are like 800, 900, okay? So single bonds between atoms are 300, 400 kilojoules. Some of them are weaker, some of them are only 200, some of them are a little stronger for, almost 500, but for the most part, they're like 300, 400 or so, okay? So those are our bonds. So that was step 2. So step 1, we said, draw Lewis structures. Step 2, look up the bonds, right, in the Alex data table so that you have the delta H values. And then you do some calculations, right? So now let's do the reactant calculations. So I'll do that here. Now, be careful with your counting, right? You've got a carbon chlorine bond, but there's 4 of them. 1, 2, 3, 4. So it's 4 times 326. And then you've got an HH, there's only 1 of them there, so plus 436. Okay, so 4 times 326 plus 436, and you get 1740. Okay, then you do your products. Okay, products, we have CCl. Well, we already did CCl. How many of them are there, though? There's 1, 2, 3. There's only 3 of them. So 3 times 326. And then you got an HCl, right? HCl or ClH is right there. So plus 431. Okay. So do the reactants, do the products. So 3 times 326 plus 431, and you get 1409. Okay. And then we said step 4 was reactants minus products, not products minus reactants, but reactants minus products. So that would be 1740 minus 1409. Now look at this one. This one is what, 331 kilojoules per mole. These are all kilojoules per mole. Okay. Endothermic. So what that means is that overall, in order to get this reaction to go, you'd have to put in at least 331 kilojoules of energy. It's endothermic. You got to put energy in to make this bond, to make this reaction go. Okay. The ones that are exothermic, you don't have to put in energy. They do it all by themselves. Okay, let's see this question. Nicole, let's see what you say on the chat. Do you need to add a CH? Oh, did I forget the CH? Did I forget the C? I forgot the CH. Thank you so much, Nicole, right there. I completely forgot that. You got the CH. We got to add that in there. Thank you. So that's on the product side. So let me do this because this is going to be wrong. So 431 was the CLH, right? Okay, so let me put the 431 later. Okay, so let's go back over the product. We have these 3 bonds here, but we also have a CH. Thank you. So there we go. So that's plus 413. And then we have our HCl. So our HCl is 431. Thank you. Okay, that's going to probably change the answer, right? It might actually make it exothermic, or it's going to be pretty close. Let's see. So now let's do the products. 3 times 326 plus 413 plus 431, and you got 1822. Okay, so now reacted, it's going to change our answer, right? Thank you, Nicole. Very good. So that's 1740 minus 1826. So now it's negative 86. Okay, so our answer, that changes it dramatically because now it's exothermic. So it's going to release 86 kilojoules per mole, right? That's our delta H now. It's negative, which means that it's released. It's going to be exothermic process. So we don't have to put energy into this reaction because it produces 86 or releases 86 kilojoules of energy. Very good. Okay. Now let's see. Does it make sense to do another one? Let's see. Let's do one more. So I'm going to do one that's combustion. So again, everything is gas phase. So this is burning natural gas to get carbon dioxide and water. Okay, I'm going to leave the states of matter out, but everything's a gas. All of these values in the table are gas phase. Okay. So let's draw the Lewis structures first. Some of them are pretty easy, right? CH4 is an easy one. We've done that before. Carbon at the center, 4 hydrogens. Then you have oxygen. Okay, now let's go through oxygen. I know I've done it before, but let's try it again. So you have 2 oxygens. So you know you got at least 1 bond. Okay. Oh, I was going to say put these in parentheses, right? There we go. Okay. So how do we do oxygen? Well, oxygen is group 6A, which means it has 6 valence electrons, but there's 2 of them, so you got 12. We've already used 2. So you have 12 valence electrons because each oxygen is in group 6A. We've drawn 1 bond, so now you're down to 10. So what do? You put lone pairs on each atom till you get up to 8, but you have to stop now. I had to stop right there. I couldn't get that oxygen on the right up to 8 because I ran out of electrons. I put another 10 electrons, so we're out of electrons, right? So don't just add lone pairs till they get up to 8. Count the number of electrons you have to work with, and if you run out of electrons, you got to stop. Now, here's what we do, just kind of what we talked about before. If one atom has 8 and the other one has fewer than 8, you push a pair from the one that has 8 to form a bond so that they both have 8, right? Because that pair will now get counted by both atoms. So what you end up with, let me erase this, is a double bond between those 2 oxygen atoms and 2 lone pairs now on each atom. Okay. Now, how many are there? 2. So I'm going to put a 2 there. Okay. Now let's do the product side. Carbon dioxide. Carbon at the center, 2 surrounding oxygens. We're going to have to work with this one a little bit too. Carbon is in group 4A, so that's 4. Oxygen is in group 6A, so that's 6. So that's 16 electrons. We've already drawn 2 bonds, so we subtract 4 electrons, and that's 12. Now with this one, 12 is a multiple of 6, so you're going to be able to get each surrounding atom up to 8. But then you'll run out, and now we're out of electrons. So now the issue is the carbon only has 4. It doesn't have 6, it only has 4. So we push a pair to give that carbon a pair of electrons, and that's going to give it 6, but it needs 8. So you actually have a couple possibilities. You could push another pair from that oxygen, or you could push a pair from the other oxygen. In general, what you want to do is 1 pair from each oxygen, because what happens is if you push both pairs from the same oxygen, that is going to give the formal charge of the oxygen +1, and the carbon's going to have a formal charge of 0. But we want 0 formal charges. So you're better off just pushing 1 pair from each oxygen. So if I push 1 pair here and 1 pair here, each oxygen will have a formal charge of 0, and the carbon will also have a formal charge of 0. So distribute them kind of equally. Okay. So let me erase this. Here's our new Lewis structure. We now have double bonds. Okay, and then you've got, okay, now, like I said, you got to put these in I recommend putting them in parentheses. So I'm running out of room, right? So we have parentheses on here. And then you got 2 waters. Well, water's easy. So 2 waters. Water's an easy one. So 2 lone pairs on the central oxygen. Okay. So there's that's really your first step, right? Is to draw the Lewis structures. Okay. Once you've drawn the Lewis structures, okay, then you want to look up the values of the delta H values, the bond enthalpies. So bond enthalpies. This is in the units of kilojoules per mole. Okay. And so we have several bonds. So we've got a carbon hydrogen. We've already looked at that one. That one's 413. We've got an oxygen-oxygen double bond. So make sure you look that one up. Oxygen-oxygen double bond is 495. And try not to make the common mistake of saying, oh, I'll just look up oxygen-oxygen single bond and multiply it by 2. Doesn't work that way. Oxygen-oxygen single bond is only 137. So 2 times that would be 274. You'd be way off. So make sure you get the right bond, a double bond between the oxygens. Okay. So this one, we're not doing that now, right? We're not doing those. We're doing these ones down here. Okay. Okay, what other bonds do we have? We have a carbon-oxygen double bond. Okay, let's look that one up. That one. I think this might be the one I made a mistake when I did my initial discussion of this. So just off the top of my head was putting the numbers down. It's actually 799. I think I might have put 395. And so if I put 395, that was an error. It's actually 799. 395 was the value of delta H of formation for carbon dioxide. Okay, so this is 799 is the proper value. Again, they're all positive. Bond enthalpies are positive. And then you've got OH. And that one we've already seen is 463, right? Okay, so now we've got our bonds. So step 2 is you look these values up. Step 3 is you add them all up for the reactants and you add them up for the products. So the reactants are these ones here and these ones here, okay? So what are you going to get for reactants? Let me do it over here. So the reactants, the delta H would be, okay, you've got a carbon hydrogen, which is 413, but there's 4 of them. So it's 4 times 413. And then you've got an oxygen-oxygen double bond, which is 495, but there's two of them. So 2 times 495. Okay. Next thing is products. Okay, so step 3 is you just add up all the bonds for the reactants and products. So 4 times 413 plus 2 times 495 is 2642. It's a pretty big number, you know. So you might think this is actually going to be an endothermic process because the bond enthalpies of the reactants are so strong. But it turns out they're even stronger in the products because of that 799 for carbon dioxide. Carbon dioxide is a pretty interesting molecule. So let's be careful with this. On the product side, you've got carbon and oxygen as a double bond, but there's 2 of them. Right? And again, don't fall into the trap of looking up CO as a single bond. It's C double bond O, and there's 2 of them. So 2 times 799. Okay, that's right here. And then you've got the water. We did the water before, but take a look. There's 2 of them there, but you've also got 2 waters. So that's one of those cases where it's 2 times 2. So that would be 4 times 463. So even though this is a pretty big number, this one's going to be bigger because you have so many oxygen-hydrogen bonds, and you have these 2 really big energies of carbon dioxide. Okay. So 2 times 799 plus 4 times 463, and you get 3450. Big number. So actually this is combustion, right? Hydrocarbon plus oxygen to form carbon dioxide and water, that's combustion. That the bonds on these products are so strong added up together collectively that when you do your reactants minus products, you're going to have 2642 minus 3450, right? And so you're going to get a big negative number. So 2642 minus 3450, and you get negative 808. Good fuel. That's why we, natural gas, right? The history of natural gas is that it is formed in the same places that oil is formed from the decomposition, the geologic millions of years of decomposition of organic matter, usually plankton in the oceans or entire forests, ancient forests from the days of the dinosaurs and before, right? And so methane is a gas and it's formed in this process, but it gets trapped by underground. So when you stick a pipe, into the earth deep enough, what happens is that gas will come up the pipe and escape. So it used to be they didn't really want to use it. They just wanted the petroleum. So they would just burn it at the top. It burns, right? So that's burning. And you would have your delta H is minus 808 kilojoules per mole, exothermic process. But now it's actually because that's a lot of energy. You're burning energy and you're not using it. You're just burning it off, right? So now actually they collect it. They collect the natural gas, and then it's a gas, so it's not easy to transport. It takes up a lot of space. Remember, gases are low density, so it takes a big container to transport gas. So what you do is you cool it down to a low enough temperature that it liquefies. Okay, and so they call that liquefied natural gas. It's very popular. They call it LNG. And so the MTA buses, some of them now, are, instead of using gasoline or diesel fuel, they use liquefied natural gas as a fuel. It works very well. Okay, a lot of energy coming out of there. Negative 808 kilojoules per mole. Methane doesn't weigh very much. It's 16 grams per mole, so it's pretty light. So not much weight, a lot of energy. That's a high energy density, the amount of energy divided by the amount of mass that you're having to carry around, right? Because carrying mass requires energy to move it. And so the lighter your fuel is, the more energy you can use to actually propel the device, like a bus or an airplane. Okay, so there you go. So there's your bond enthalpy, or bond energy, as Alex calls it. What I want to do at this stage now, since that's the end of chapter 8, and you guys do have a long time until this one is due. It's not really due until, let me see if I can bring this up. It's not due until June 6th. So you got a couple weeks here. So we're a little bit ahead of the game. So what I'm going to do is I'm going to go ahead and just introduce, just for a moment here, chapter 9. We're going to have plenty of time. There is a holiday coming up. May 31st is Memorial Day, so there won't be a meeting. Well, that doesn't even affect you guys because we don't even meet till Tuesday, Wednesday, Thursday. So we have a lot of meetings left. So I'm going to spend some time talking about chapter 9. These are extra credit assignments. So what we're going to do in chapter 9 is we're going to talk, this is called chemical bonding 2. Is we're going to talk about several topics. One is what's called molecular geometry. And this ends up being important for biology people. So molecular geometry is the shapes of molecules. So what we're going to want to do is we're going to want to figure out whether molecules, so here's an example. If you look at the Lewis structure of water, from that, it's not clear what the shape of the molecule is. We might think it's linear because we've drawn it as a straight line, but that's not correct. It turns out it's not linear. It turns out the water molecule, more accurately, has this shape. This is called bent. Sometimes people call it V-shape, but the more common name is bent. Okay, and there's an angle between those two bonds. So if you start here, the first bond on the left between oxygen and hydrogen, and you sweep out an angle till you get to the next bond, which is the hydrogen on the right. That's called the molecular angle, or the bond angle. We actually call it bond angle. So that's the angle between the two closest bonds in the molecule. And that angle for water is, it's actually known very well. I'm going to write it out as 104.5 degrees. Okay. Now, how big is that angle? Let's think about it for a moment. If you have a right angle, that's 90 degrees, right? If you have a straight angle, so, moving across here, that's 180 degrees. So 104.5 is a little more than a right angle, right? It's around 14 degrees more than a right angle, so a bit more than that. So that's called the bond angle, 104.5 degrees. So it's not a straight line like you might think with a Lewis structure. The Lewis structure doesn't actually tell us the shape of the molecule. It tells us the arrangement of electrons. It tells us whether we have single, double, or triple bonds. That's very nice, but it doesn't give us the shape of the molecule. So what we're going to do in chapter 9 is we're going to look at how, very simple theory, very simple model, which allows us to predict the shapes, the geometries of simple molecules. And then from that, we're going to be able to look at some of their properties. The shape of a molecule actually affects its properties. We all know, for example, that water is polar, right? It has a dipole. Okay, that means it has electrical properties. And of course, those electrical properties of water are very important in terms of its shape. If it, the structure of ice, for example, the actual liquid water actually has a structure. So even though it's a liquid and can flow, there's actually a molecular structure to how the water molecules interact with each other, which allows them to ionize things, right? Allows them to dissolve ions, electrolytes, allows them to dissolve sugars and DNA and proteins and carbohydrates, but not other things, not lipids, for example. So all of those kind of chemical properties or physical properties of water, much of it is due to the shape. If water were linear, if it really were a linear molecule, it would be a very different kind of molecule. It would be a lot more like carbon dioxide. you wouldn't even see liquid water most likely. You would have, like we have dry ice, you don't see liquid carbon dioxide. It's either a gas or it's a solid. Water might actually be the same thing if it were linear. So the properties of water are owing to a large extent based on the geometry, the shape of the molecule. So I will cover that next Tuesday. And then we'll go into a couple of other topics on Tuesday. And I'm just going to go through chapter 9. And if you do have questions, if there are problems that you're struggling on for chapter 8, we also will have time to do that. So you can certainly ask any questions. And if you aren't able to make the live lecture, but there is a particular problem you're struggling with and you'd like to see it done, then you can just, send me a photo of it or ask a question, text it or something like that. And then I can make a little bit of time next week to do that as well, because we will have time to do these topics in chapter 9 and answer any questions that you have. Okay. Thank you. And so that's our last meeting for the week, but have a great day. Reach out to me if you have any questions, and I will talk to you later.
Oh, Professor, answer a quick question. I spoke to you earlier and you told me to remind you